Okay, this is Lesson 10, Activity 2. It's titled Similar Triangles on the Same Line. And this is actually towards the middle of the activity. I just want to show you where we're going. We're going to work with these three triangles. There's a small triangle right here, a large triangle right here, and a medium-sized triangle right here. So we're going to demonstrate or show that all of these angles are congruent and that all of these triangles are similar, because we're going to start using what we just got done talking about. We're going to look at ratios. We're going to look at the ratios of the vertical sides to the horizontal sides, and we're going to start talking about this thing called slope. So just want to give you an idea of where we're going. So let's go back up here to the beginning. It says similar triangles, longest side on the same line. So notice that for each of these triangles, the longest side is on the same line. So how do I show you, or how do I prove, or how do you prove to me that each of these three triangles are similar triangles? A couple different ways. Actually, there's three ways that I can think of doing it. So this is the largest triangle, and what I'm going to do is make all three triangles nested. So point A is going to go to point C, and point F here for the small triangle is going to go to point C. So this is triangle ABC right here, and just moved it up, translated it up so that A goes to C. And this is triangle FGH, and so point F goes to C as well. And so if I can do that, and I can do that, it's a rigid transformation, it's a translation, so the angles are not changing size at all, they're just moving through the grid. And now if I can show a dilation that takes triangle FGH to triangle ABC, or triangle CDE, then I can demonstrate that those triangles are similar. All right, so rigid transformation, translation of A to C and E to C. All right, so dilation, and I can show you that. The center of dilation is this point that's shared in common between the three triangles. And if I use a scale factor of 2, I'm going to take the pink triangle to this blue triangle here. So FGH to ABC. So triangle FGH is going to go to triangle ABC, the scale factor of 2. So each length is doubled. It's twice as long. And I put the midpoints of this size here just to add one more point to show you that the scaling is correct. All right, scale factor of 4. It's going to take triangle FGH to triangle CDE with the scale factor of 4. It's 4 times as long. So this is 2 units, 4 units, 6 units, 8 units. 4 times as long this way. This is 1.5. 4 times 1.5 is actually 6. This is 1.5 units, 1.5 units, 1.5 units, and 1.5 units. So in fact, those triangles are similar. All right, so another way to show that the triangles are similar is to look at the angles. If I can show you that 2 angles are congruent, then those triangles are similar. We've had this in the past. If 2 angles are congruent between 2 triangles, then the third angle has to be congruent, because that third angle, remember, has to make up the sum of the degrees to equal 180 degrees. So if the first 2 triangles are congruent or equal, then that third angle has to be congruent or equal, because it has to be the same amount in both triangles to, once again, to equal that 180 degrees. Well, look at these 3 triangles. One of the angles is clearly congruent. It's 90 degrees. So it's this angle here, here, and here. So now all I have to do is show you that one of the other angles is congruent, and then I can prove that these triangles are similar. All right, so one way to do that is to translate angles. I'll show you that in a second. Another way to do that is to use this idea of alternate interior angles. So 180 degree rotation combined with a vertical angle, and we're going to review that in just a moment. So these are the 2 ways. One is to translate it, and the other is to use alternate interior angles and vertical angles. All right. So these are parallel lines. This is the side of the smaller triangle, and this goes to the vertice of this. Oh, actually, it's the side of the larger triangle. Let's say it that way. Yeah. And this line right here is the transversal. Remember, a transversal is a line that transverses, it goes across two lines that are parallel, and it does that. So we're going to use the transversal and these angles that are formed with the transversal, which is the long side. Transversal is the long side of these triangles, and use the angles that are formed with the parallel lines, which is the other side or another side of the triangles, to show that they are congruent angles. So this angle right here is congruent to this angle. I'm going to tell you why in a moment. And this angle also. Okay, one of the first things that we can do is just use a translation. So I can move this angle and translate it here, not changing the side. It's a size, it's a rigid transformation. So this angle is congruent to this angle. All right, so that's it. So I have two angles that are congruent. This angle is congruent to this angle, and this 90-degree angle is congruent to this 90-degree angle. Therefore, this third angle up here and up here they have to be congruent because they have to add to 180 degrees. So these two triangles, as well as this triangle down here, and we'll get to this in a little while, are similar triangles. All right, the other way is to go back to rotating this 180 degrees. So if I rotate this 180 degrees, the center of rotation is right there. Rotate it 180 degrees over to here. This angle is going to be equal to this angle. Again, it's a rigid transformation, not changing the size of the angle. Remember, when you rotate something 180 degrees, the corresponding points are on a straight line through the center of rotation, opposite of each other. So this C is going to rotate to F, and these are called alternate interior angles. So this angle is equal to this angle. It's a 180-degree rotation, and we've been through that before. You need the parallel lines and the transversal, and we have that. All right, so I'm here, but I have to get to here. So how do I get to this angle right here? Well, it's a vertical angle. We'll get to this angle in a moment. So if you take this angle and you go through this intersection to this side, it is a vertical angle. So this angle is the same as this angle. We already know that because the translation. It's just another way to do it. And I actually happen to like the 180-degree rotation, the alternate interior angles, the best way. And then the vertical angle. All right, so notice that this angle down here is a vertical angle with this angle. So if I go through this intersection, vertical angle, so these two angles are congruent. All right, so now we're going to get to this triangle down here. Well, how do I get this angle to here? Now again, I could just translate this angle down, and it shows that this angle is congruent to this angle. I just got done saying I like this alternate interior angle idea. So I'm going to rotate this 180 degrees, rotate it around. It's going to land right here. This is the center of rotation. This point goes to here. This side ends up being parallel with this side. So this angle is in fact congruent to this angle. So there you go. Two angles, this angle and this angle, are congruent, and this angle and this angle are congruent. So it's two pairs of congruent angles. Tells me that these two triangles, as well as this third triangle, they are all similar. Okay, the idea that they lie on this transversal, the long side lines on this transversal, we're going to get to using that in a little while when we talk more about slope. All right, so we're going to go back and look at the ratio, look at the quotients of the vertical sides compared to the horizontal sides of each triangle individually. And those ratios between, we did this before, the ratios of within an angle of two sides, if that's equal to the ratio of the corresponding sides within a triangle, if that ratio is equal to the corresponding sides, the ratio of corresponding sides of another triangle, then those triangles are similar. Kind of messed that up, sorry. All right, so we're going to take the vertical side and we're going to divide that by the horizontal side, or at least look at that ratio. So it's the vertical side divided by the horizontal side, so it's 3/4. So every 3 units you move along the vertical side, this one right here, for every 3 units I move along the vertical side, I'm going to move 4 units along the horizontal side. That's the way eventually we'll talk about it. All right, so if I move 2 times 3 units, I'm going to move 6 units up along the vertical side. It means I'm going to move 2 times 4 is 8 units along the horizontal side. So a ratio of 6 to 8 is the same as a ratio of 3 to 4. And they want to use division. They want to talk about quotients. But I want to talk about ratios. In a little while, we'll sort out which is better. I'm not really sure. All right, so vertical side is 1.5 units. Horizontal side is 2 units. So that ratio, that comparison is 1.5 to 2. Well, 1.5 times 2, you're going to get rid of this half. So 2 times 1/2 is 1. And so you're going to end up with hold on here for a second. It's 3/2. So 2 times 3/2, get rid of the denominator, the 2, end up with just the 3, and 2 times 2 is 4. So this 1.5, a ratio of 1.5 to 2 is the same as a ratio of 3 to 4, because you're multiplying 1.5 times 2, same as multiplying 3/2 times 2. So 2 times $1.50 equals $3, for example. And 2 times 2 is 4. Sorry about that. So for similar triangles, the ratio of 2 sides within a triangle, so the ratio of the vertical side to the horizontal side, equals the ratio of the corresponding sides within the similar triangle. And the vertical side compared to the horizontal side, that is called the slope. Whenever you look at how far something moves in a vertical direction compared to how far something moves in a horizontal direction, that's called the slope. I'm going to look at that in just a moment. And these triangles we're going to call slope triangles. So these triangles are all similar. So when you take triangles and you put them all along the same line, the long side all along the same line, those are called slope triangles. All right, so we're going to work on this more.